there might be some uncertainty involved. The outcome of an interaction will depend on the actions taken by two or many more players if they are involved. So we can think of a market game where firms set prices, so the outcome, so how much they will sell of their product and for how much, or let's say for how much they will sell of their product will depend on the price setting on both sides. The plan for the webinar is very, let's say, simple and short. I will start with discussing some ideas about solutions to games, and then we'll move towards the case that I asked you to solve, Yaki and Zenit. And this will be a case where some things in the game will be changed. And in the third part of the webinar, I'm going to talk about other ways of changing the game of business, and we conclude with discussing the Polaroid versus Kodak case, so their battle in or war in instant photography market. So let me start with something that you actually assumed I believe is the idea of a game. So interaction, actions taken by both sides, and we usually say, or this is typically done in order to solve a game, so in order to answer how this game will be played, it usually starts with looking for a Nash equilibrium. So Nash equilibrium is a strategy profile, one for each player. You can have a game with many more players. In the textbook, we had only 2 players usually, and so one strategy per player, and with a certain characteristic. So a situation where nobody can be better off by changing his own strategy, keeping the strategies of others constant. So if this is a Nash equilibrium is a solution, then the question one would need to ask is a Nash equilibrium an obvious way to play a game? So let's have a look at game 1. In game 1, we have 2 players. In the normal form, you have the payoffs. You should understand how they work. So the first number is the payoff of player 1. The second is the payoff of player 2. So what are the Nash equilibria of this game? When you look precisely, the 2 Nash equilibria, there are 2 Nash equilibria in pure strategies. This is the action 2 of player 1 and action 1 of player 2. So this is Nash equilibrium 1. And the other is action 1 by player 1 and action 2 by player 2. We have 2 Nash equilibria. So if a Nash equilibrium is an obvious way to play the game, it's not that obvious because we have 2 outcomes, 2 possibilities. However, here, this is sort of a coordination game where we can imagine that because in one of the Nash equilibrium they get the highest payoff, they sort of, the players will coordinate to play the action 2, action 1 Nash equilibrium, and both get 15 units of payoff. So even though many multiple Nash equilibria, we can find a way to play. However, if I change the game a bit, so looking at game 2, and again we have 2 Nash equilibria that you can convince yourself are in fact satisfying the definition. Now the situation is changing a bit, because of course we have again a situation where one of the Nash equilibria is Pareto superior, so they both get 15 units of payoff. But here the coordination is not that obvious. Why? If you think now, if you are player 1 and you think what player 2 is going to do, you look at the strategies he has or his actions. So action 1, he might win 15, but he might also lose 10. In action 2, he might win 10 or 5. So this action is actually a so-called a secure strategy, because the minimum payoff he can get is 5. In the other case, he can lose something. Now, if this is obvious to play 15-15, it's probably not anymore so, because what will happen here is clearly, if you are player 1 and you think that player 2 might go for his secure strategy and play action 2, you would probably think of playing action 1 instead of action 2, right? Because playing action 2 might make you lose 10. So this is risky coordination, and just to illustrate that it's not that simple and obvious to play a Nash equilibrium. If you have one, it's a different story. But even then, the question one would need to ask, and I do it provocatively a bit, because in most of the cases people just look for a Nash equilibrium to find a way to solve a game. So I would ask the question, what is required by a Nash equilibrium? So what do we need? So the thing that it's required is, first of all, the players, they have to share the understanding of the game. So they have to know there's another player, they have to know the actions of the other player, they have to know the preferences of the player, and they should also have some concept of rationality of the other player. It's called common knowledge of rationality, meaning that it's not only that I know that the opponent is rational, but I know that he knows that I am rational, and so on and so forth. So it's not that simple and straightforward, but this is what we will require. If any of the requirements is not satisfied, we might have a problem. But still, the question stays how to find a Nash equilibrium. The obvious one way is to look at all possible strategy profiles. So here we have 4, we check 4 and find which ones satisfy the Nash equilibrium condition. It might be slightly easier for games with sequential structure, because we know that such games can be solved using what is called backward induction, at least some games of sequential moves. The sequential moves make the structure more, or make it richer, in the sense of that some information can be acquired on the way. So for illustrating the backward induction at work, I would like to briefly introduce the Stackelberg duopoly. Imagine a situation, a market situation where you have 2 firms. Each of the firms has to decide how much to produce. So they decide about the output. They can go for either 15, 20, or 30 units of output. And this is done sequentially. So firm 1 moves first, and firm 2 follows. What you see in the last line are the profit. The red letters are the profits of firm 1, and the blue numbers are the profits of firm 2. And the idea behind the profit, just to make sure, of course, if they sell a product that is homogeneous, the more they produce, and given some demand on the market, or market demand function, the higher the quantity, the lower the price. So if they both produce a lot, so for instance firm 1 and firm 2 produce 30, they don't get any profit at all. But if one firm produces a lot and the other little, that means less demand, higher price, and higher profit. So this is what we obtain here. So how does the backward induction work in this particular case? So we start in the last point of the game. So here the last to move is firm 2, and we see what happens, what would firm 2 do if firm 1 decided to produce 15. We look at the payoffs of firm 2, and the highest in this case is 1,000 producing 20. We do the same for responding to firm 1 producing 20, and the highest payoff is 800 from producing 20, and if firm 1 produces 30, firm 2 is producing 15 and maximizing profit. Now, in the next stage, what happens is that firm 1 assumes that firm 2 is rational, so that firm 2 is maximizing the profit of the company, and knows what will happen in the 3 different scenarios. So firm 1, deciding between 15, 20, and 30, has to look at the case of which one leads to the highest profit. And we see that given the play of firm 2, the highest profit would be from choosing 15, and we'll get 30, we're getting the 900. So the red numbers are the payoffs of firm 1. So what we get a backward induction outcome. We also can show that this outcome is a Nash equilibrium. You should be able to do it on your own. But here I just want to make sure that you understand what is the point. The point is that in order to solve it this way, you make assumptions about rationality, about something that will happen later on. Which, if this seems to be natural and easy, so let me propose you a game, a famous one, and this is the so-called ultimatum game. The rules of the game are that there are 2 players, and they have to share 100 euro. Okay, player 1 decides how to share the 100 euro, or we can say that player 1 says how much to give to player 2, and player 2, seeing the offer, can either accept it, so he takes what it's offered, and the rest gets player 1, or he can reject the offer. In this case, they both get 0. Okay, it's a very simple game, and I would like you to put yourself into the position of player 1 and try to answer the question: how much would you offer to player 2 if you were the one deciding? So you are player 1, and you have to decide how much to give to player 2. How much would you give? So please take part in the poll. So just try to, you play the game. You have the money, you can give part of it to player 2, and the rest is yours. Of course, under the assumption that player 2 accepts the offer you made. Okay, so there are no new answers, so I close the poll over here. What I see is that 60% would give at least, I'd say, could give half of the money to player 2. Someone would even give more, 2 of you. So this is where we get. So let's put yourself into the position of player 2 and try to answer the question: how much? What offers would you accept? So you get an offer of 0. Do you accept it? Do you get an offer of 10 and smaller? Do you accept it? Please choose 1. And so now you're in the position of player 2. Okay. So we have 12 answers. If somebody would like to join, then please do it. Otherwise, I would close the poll to continue with the slides. So we have 14 answers. I wait for the last one, the 15th, and we can continue. So someone who did not join yet, please go for it. Okay, so I close it. What we get here is the situation that actually it's not true that people would accept any offer, like any euro you get. Some people would only accept the offers that are very high, that give them a big share. So the 2 questions, the way you answered is actually in line with the findings of experimental literature, because it turns out that a vast majority of individuals offers between 40 and 50 euros to the opponent, and less than 20 offers of less than 20 euro are usually rejected. So we can then compare it afterwards. But this is an interesting thing. If I would ask you what is the Nash equilibrium of this game, then by using backward induction, you would arrive at the following finding. If you are an individual concerned with money, you are player 2, and player 1 offers you something, then you take whatever you get. So if you get 1 cent, 1 cent is better than nothing, right? So instead of rejecting this offer, you accept it. So any offer that is positive will be accepted. And knowing this, you doing the backward inductive analysis, player 1 decides to offer exactly this 1 cent. So this is what theory would tell us how the game is going to be played, solved by backward induction. And we have to be careful with it because this game is a very interesting example. I refer you to the literature that I have provided to the webinar, specifically the papers by Roth, Al Roth, and Fer and Schmidt. They discuss other ideas, but just to make sure that we understand, you could ask yourself, why do you offer, as player 1, offer something to player 2? If you would be purely concerned with the money, you wouldn't give just 1 cent. But it seems that there might be at least 2 reasons to give money. One is because people and you have the notion of fairness. You want to share some of the money. And you have this 100, so the fair share would be about 50-50. Or the other driver could be that you are afraid that offers that are too low, and you are predicting that this might happen, will be rejected by player 2. Because player 2 can give up some of his payoff, some cents, some euros, in order to punish the opponent. So these are the 2 factors, and the literature that I mentioned is discussing this, and probably something that is interesting to see. What is the learning from this game for our class, for our webinar, is that people are not only concerned about money. So there are other aspects, and they are not only concerned about the money they get, but they are also concerned about the money that other people get. So they have other regarding preferences, and therefore this idea of equity or inequality aversion. So another example of a game where that can be solved by backward induction, I just discussed it very briefly. The structure is there are alternating offers. Player 1 starts with, can either stop the game or pass the game to player 2. If player 2 has the chance to move, he can stop it or pass it again to player 1, and they continue doing it 100 times. So this is the entire structure of the game. The game is called Centipede because of this animal that has 2 legs per body segment that you see on top of the screen. And the interesting thing here is the payoff structure, because the idea is that if you pass the play to the opponent, you lose 1 payoff, so 1 unit, and the opponent would earn 2 units if he decides to stop in the next round. So I just, again, don't want to spend too much time, but would like to present it. If you use backward inductive analysis, and because of the idea of the structure of the payoffs, the conclusion is you should stop the game in the game should stop in the first stage. So player 1 stops the game, they both get 1 unit of payoff. Comparing it to 50-50 that they could have had at the end of the game after some rounds, it's surprising, but this is what the notion suggests. But let's say experimental findings would say that it's not how people behave. So what's the problem here? Is the problem that people are not rational, so that they, what does actually mean not being rational? We can divide it into, maybe they don't fully understand the game, maybe they cannot identify the best way of playing the game, or maybe they make mistake in implementing the strategy. So here, again, another caution for you when applying the backward inductive analysis. There are very strong assumptions made behind it. But this is like the 2 games and the 2 limitations that I wanted to introduce. So this is for the beginning. Now we move towards Jaki and Zenit case, and this is where you hopefully or had the chance to look at the case. And this is an example of a sequential game where we have 2 players, Jaki and Zenit, and Jaki has some technology that developed and this technology can be offered to Zenit, or so these are the two options that actually Yaki has: offer it to the opponent or not. And Zenit, if get the technology, can either use it in a market that is separated from Yaki's, or we can invade Yaki's market. The payoff structure is the following. The colors should help you distinguish the payoffs. The first is the payoff of Yaki. The second is the payoff of Zenit. Now, so what is the way to play the game? How would one play the game? So we could say, what is the Nash equilibrium? Okay, we can actually use the backward inductive approach, or we can try to transfer this game into a game, a normal form game. And here, what we have is the situation that in the normal form game, we put all the strategies. So Yaki can offer, or Yaki does not offer the technology, and Zenit can invade or don't invade. Okay, so the payoffs, if offer and don't invade, so we are in the upper branch of the tree, game 3. So the payoff is 10 and 10. If it does not offer, it's 0 and 0. Here you have to just make sure that not offering the technology would always lead to 0 and 0. Here I'm sure you can much faster identify the Nash equilibrium, because you would then compare the payoffs and say the Nash equilibrium over here is the don't offer the technology, and if offer the technology, then it invades the market of Yaki. So the outcome is 0 and 0. This is our Nash equilibrium, but of course there is another outcome that is much more focal in the interaction, is that they could actually both benefit from cooperating, in a sense of if Zenit behaves in a trustful manner, they can both benefit. So the way it works, actually, if you use the backward inductive argument, what we see is that when Zenit is going to move, so after getting the technology, it is in his best interest to invade, because it gets $20 million instead of 10. And knowing that, Yaki wouldn't offer the technology. So here we have to do with what is called an incredible promise, because Zenit is promising something that when it's called to move is not in his interest to do so. So Zenit wouldn't, let's say, keep the promise and don't invade. So it cannot be trusted. But clearly there is some potential to improve the profit payoffs on both sides. So of course Yaki could be interested in making this promise credible. What can be done? We look at part B of the case. So they offer a contract, and in this contract certain rules are implemented. If Yaki trust is abused, then Zenit has to pay 20 million. So what is changing in the game we had so far is changing the case of invading. After invading, when the technology is offered to Zenit, Yaki could go to court or don't go to court. Yeah? So the new option is go to court, and the payoff is calculated as getting the recompensation of 20, losing the 20 exactly, and getting the recompensation plus the fee they get from Zenit minus 12, which are the called costs. Now, here the question is, does the contractual agreement guarantee make Zenit promise credible? So I can change the question and ask, is it the best thing to do for Zenit when offered the technology to not invade the market? If this is the case, then we can say that the promise is credible. So let's do backward inductive analysis. What do we get? That if Yaki's market is invaded, then it will go to court because it gets -2 in comparison to -10. Knowing this, and assuming that Yaki is rational and will go for the case, then Zenit does not invade the market. And knowing this, so this entire chain of reasoning, Yaki would offer the technology. Because of this way of changing the game, what happened is that they reach an outcome, 10 and 10 million for each player, that was not possible otherwise. Also here we have to be a bit skeptical, because we know from a practical perspective that going to court does not always mean that you win the case. So this is also what Yaki is expecting, that there is a certain probability of winning the case, let's say 30%, and if it loses, then of course all the costs has to be paid by each of the players. So what happened? We added a new part of the tree, win and lose, with specific probabilities. Looking back at the decision trees, of course, this is very much in line. I don't use the special characters for a circle or the square, but you could also put them here. But for simplification, I don't do that. What you see over here, now what is going on to happen? This is a good question. First of all, we have to know the preferences. Yaki and Zenit will need to have a certain concept of what the opponent is maximizing. Assume that they are both risk neutral, so they are maximizing the expected monetary value. How is this game going to be played by Yaki if Zenit invades the market? Then it calculates the EMV. It's -16. It compares it to don't going to the court, which is -10. So in this case, it's better not to go to the court. And knowing this, Zenit would invade the market. If Yaki offers the technology and knows that, or predicts that this will happen, they would not offer the technology, because they would lose. If they don't offer, they lose nothing, but they win nothing. So again, as you can see, that the entire reasoning is very sensitive towards the details of the case, and the details are the probabilities are also the payoffs. So we don't talk so much about modeling, but I'm talking about the very clear idea of analyzing the game. Here we have the 30% probability of winning. We could do sensitivity analysis and say, what probability of winning would Yaki go to court when invaded by Zenit? We can calculate it. The answer is 60%, but this is what can be done. Here, a strong statement is not necessarily the fact that this is the 30% probability of winning or losing, or 60%, but it's more the belief that this will happen. The belief drives your analysis and makes you behave in a certain way. Okay, so keep that in mind for the moment. So when we talk about this, we already looked at some cases of changing the game. And the Yaki Zenit case, it's commonly known as the game of trust, because Yaki can either trust the opponent and give the technology, or not give the technology, and Zenit could respond by abusing trust, so invading the market, or respecting the trust from Yaki, and this is the other option. So I would like to show you also another game that is very similar in structure, but it gives us more a different story that we could think about, and maybe this story is also interesting for business students, namely the game of threat, or threat game. We have 2 players, and you can think about it as a market of a monopolist, and this market that can be challenged, the incumbent could be challenged by another firm. So player A is the challenger, and player B is the incumbent, the monopolist. So if there is a new firm entering the market, could either challenge the company or the incumbent, or could stay out, and player B, the incumbent, could fight or could acquiesce. Okay, so accept the new entrant and share the market. If you look at the payoffs here, of course, the best for the incumbent is when the challenger does not enter. So this is the number 2 for payoffs. And the worst case is when challenged to fight, because fighting is costly. And how can we think about fighting? What do we mean? Fighting could be price war. So we could think of reducing the price using either limit prices, so prices equal to the marginal cost, or predatory pricing, so that the price is below marginal cost, or we can think of other ways of limiting the profit of the opponent if they are part of the same, let's say, supply chain. They could squeeze the margin, for instance. Now, in this game, when you think about it, it's a game of threat, not a game of trust. Even though they are different, they have something in common, and the common aspect is the idea of credibility. So if you think about this game, I could ask you to solve it. Okay, so what are the Nash equilibria? I do it here for you. So there are 2 Nash equilibria. One Nash equilibrium is the one that we get by backward induction. So if the player B is challenged, will acquiesce, will get 1 instead of -1 when fighting, and the challenger, knowing that, will challenge the incumbent and will get 1 instead of 0. So this is one Nash equilibrium, and the other one is this: that player 1, so player B, says it will fight whenever the market is entered, and player A will stay out. Okay, so why it's a Nash equilibrium? Because if player A knows that player B will fight, he decides between having a payoff of -2 or 0 if it's not entering. So this is the best to do. And for player B, the checking of a Nash equilibrium will be on the other side. It will not be challenged, so it doesn't matter. But the threat is important here. Okay, so fighting is a threat. What do you think? How do you think which of the Nash equilibria will be played? And for this, I have prepared an opinion poll that I would like you to take part in. Let me think. I think it's this one. So, what do you think? Nash equilibrium 1, Nash equilibrium 2, maybe none of them will be played, or you would like to provide some other comment. So what do you think? Okay. So we have already 17, 18 responses from 20, altogether 26 participants. I close it now. We have about 50% of Nash equilibrium 2, and the rest, just like one of you decided to say that there will be none of them will be played, and the rest will say one will be played. So you say that Nash equilibrium 2 will be played, so it will be challenge B, and then it will acquiesce. Okay, if we now accept the idea of backward induction, this is what will happen. The difficult thing in the second equilibrium is it includes an incredible threat. So when is asked to move, like when challenged, it doesn't pay off to really fight. It could acquiesce. But I would like to provide a broader perspective. It's not modeled here in this particular game, but you can think about fighting. Even though it is costly for this particular situation, for this interaction with this challenger, you may think of having a signal sent towards other potential entrants. So if by this, so losing in this particular game, it may send a signal to others in the future, so you lose maybe 2 or -1, so you lose 1 unit of payoff, but you might secure some in the future. But this is just a side remark, because I changed the game in my description. So here, again, we have an incredible threat, and we have to think how to really cope with that. If player B would like to really keep player A outside of the market, I would need to think about changing the game somehow. So how to change the game. So the big question to be asked is how to make an action credible. So how can we make an action credible? This applies to both games. So the trust game and the threat game, and one can actually change the game, redesign it so that when you are asked to move, this promise or the threat is the optimal action. So you have to change the incentives ex post. So how can we do it? Logically, there are just 2 possible options. You either improve the payoffs from taking this action. So if you think about the threat game, so you can think of increasing the payoff from fighting, or you can worsen the payoff from other actions. And in the typical case, if you think about market interaction, it's much more difficult to improve the payoff. So it's much easier to decrease the payoff. So this is what would usually be done. You can worsen the payoff. Now, if you look at the trust game and knowing the structure, what it would mean is that abusing trust should be that player B should be worse off. So I would subtract 2 units of payoff, and therefore when player A trusts player B would later on basically be better off by trusting, or let's say treating A fairly than abusing. Okay, how can this be done specifically? Okay, so one example we saw in the Yaki Zenith case. So there might be a contract. Okay, so by contract, where we write some contingencies and punishment or fines, you can receive obtain this result. Okay, so this is the way it works. Of course, you need a third party that will enforce the contract, and this might be in many situations very difficult or impossible. So you can also think about structuring the game so that a player A punishes player B for misbehavior. And I would like to give you an example, and this has to do with Intel. They developed their chip 086, and they were supposed to get some partners. So they wanted to have some firms developing hardware and software that will be compatible with this chip. So they promised that they will keep the price of the chip low, so that when these firms join, they will afterwards also keep the price low, so they can benefit from the market. The risk there, of course, is if Intel is the only producer of the chip and they produce architectures and develop software that is only compatible with this particular chip, so they have a hold up problem, and Intel wanted to somehow convince the potential partners, that it will not do it. So instead of writing contracts, what they did, they licensed the production of the chip to many firms. So then the potential partners know if Intel is going to increase the price, they could still afford the cheaper chip from others. So you can think about changing basically the game by licensing the. So this is also costly, of course, was costly to Intel, but this was what they did. The third option is you can think of social sanctions. Decreasing payoff by social sanctions is if you think about someone promising to do something publicly. You can think about the politician who says, I will fulfill a certain promise, and if he's not fulfilling the promise, he will lose supporters. So social sanctions can be useful or may work in some situations, probably that they don't work for all possibilities. So this is one way to changing the game. So what is the alternative? An alternative approach to changing the game, and now I move more towards the threat game. We can think of firms, and one way to make this fighting aspect more credible is by limiting its kind of choices, for instance, or changing the payoffs respectively. So, for instance, a firm, let's say the one firm A, so firm B, would, for instance, choose a technology that has very high fixed cost. Okay, a very high fixed cost that could happen by turning a variable cost into a fixed cost when they oblige to buy, let's say, raw materials for a very high price today, not making it flexible for the future. So they buy all the materials today, so they kind of block a lot of money, so they have a fixed cost. Another way of doing it could be installing a technology that has a very high capacity. So in order to produce profitably, they would need to produce at a large scale. So in this case, it would mean they have to keep the market for themselves. If they don't, then they cannot cover the variable and then part of the fixed cost. So you can think about further ideas. So we could represent the situation using the following game tree. When you look at the upper part of the game, it's like it was before. So this is what is the optimal technology. So there is, I call it optimal in quotation marks, which will become clear in a moment. So for the lower part, the things that changed are the payoffs of firm B, because by introducing the very high fixed cost technology, it does not change the incentives of player A, so the red numbers stay the same, but it changes the payoffs from player B. So I subtract some numbers, -1, like you subtracted some values. Here, it's not about the values really, it's more about the way of organizing your ideas and structuring them. So what do you see if you try to analyze it is in the upper part of the tree, backward inductive analysis would make player B acquiesce when challenged, and then player A would challenge. In the lower part of the tree, because of the changed incentives, because of the high fixed cost technology, the firm would rather fight in order to survive, and player A wouldn't basically challenge the player B, and of course player B choosing between the optimal technology and the high fixed cost technology would decide to take the as you can see, the high fixed cost technology because they have higher pay of 1.5 instead of, or in comparison to 1. Now, the interesting thing you probably recognize is that this is a really clear case of market barriers or market entry barriers. And the usual idea of market entry barriers is this. Firms try to limit access of the potential competitor to access to resources, to distribution channels. And this idea proposed here is a different one. Actually, this one says you can get the same result. You can create an entry barrier by changing your own technology, so taking an action. So you decide to do something that is worse for you because the high fixed cost technology might be bad for you, but after all, this is the optimal strategy because this brings you a better outcome on the market. So this is why the word optimal was in quotation marks in the upper part of the tree. So of course this is not a risk-free strategy because if this is not communicated to the opponent, if it's for some reason unclear, you decide for a high fixed cost technology and the challenger challenges, then it's even worse because then it looks silly or irrational or stupid to decide for a suboptimal technology. So it is optimal as long as it works. If it doesn't, we have a problem. So this is the idea of changing the game this way. Another example of changing the game is the a way of changing payoffs for all the players. And the idea is so that in some cases players can change the payoffs of their own and others, but for their own, this impact of the cost change is less severe than for others. What could be the situation? If you think about big companies, for instance, Monsanto or Dow, or Monsanto, they promote very high environmental standards, so that they stick to the standards, which is obviously costly. It costs money. So why do they do it? So what is the rationale? One rationale is, of course, they want to send a costly signal to the market. We care, we spend money, we support the standards. But another idea would be to understand it as changing the game, so that also other firms, smaller competitors, for them fitting or sticking to the standards is much more costly, so that they change the game so that the others will suffer from it even more. This situation could be represented by the following game tree, and you see the payoffs of both players changed, and except for the situation here, if lower part of the game, if the environment does change and the firm A does not challenge B, we stay with 0, because if they don't want to stick to the game, they don't have to spend money on fulfilling the standards. How is this game going to be played? The complex one. Of course, using backward induction, it seems to be simpler to analyze it. So let's have a look at the upper part. This is what we know. A challenges B and B acquiesces. In the lower part, however, it's player B will acquiesce as well. However, because of the payoff or the incentive change, player A will not challenge. And comparing the two outcomes, 1 and 1 and 0 and 1.5, for player B, it's better to change the environment and change the costs. You can think of a number of examples, and I refer you to the chapter by David Krebs. I think it's chapter 22 on credibility. You can find some further examples over there. Now I would like to move toward the case that I asked you to look at, Polaroid versus Kodak. So we have two firms. Polaroid is the let's say, initial developer of instant photography. They exist from the 40s, and they were active in the market for 20 and something years. But they were, even though they had this niche market, they were not very strong comparing to Kodak. Kodak was a huge company with extremely huge financial strength. And what happens in the 70s is that Kodak announces developing their own line of instant photography cameras and their own film. Just like a side remark, they were producing the film for Polaroid before, so they were they were in very close contact to each other. So what they do, they announce that they will join the market. This is, of course, a case of an incumbent and a challenger, and we discussed it so far. So the question here is, how is it going to be played? So the way it was built up, we can think of a situation that Kodak, because of this relationship with Polaroid, they made sure that they want Polaroid to survive in the market. So they committed, or let's say they sent some signals and did things carefully so that to assure the opponent that they will survive in the market. So because of the numbers, as I mentioned before, the financial strength, it looked like we have the classical threat game. In the classical threat game, the backward inductive solution will be played. Kodak enters, Polaroid acquiesces. That's it. So we could look at the game from this perspective, right? So we have K standing for Kodak, P for Polaroid, and we know the way it should be played is this, right? So this is the situation that as it was expected to happen. If Polaroid is interested in changing the game, can use one of the examples that we discussed before. So they could change the payoff somehow. So they actually, of course, considered different strategies. So what they did, they started with some, let's say, social statements, or social norms, and committing themselves to the market. And the founder, Edwin Land, he quoted like in an emotional statement that they will stick to the market. This is what you can read over here. That for them it's the entire world. For Kodak, it's just another market that they are entering, and they will protect it at any price. So they were already signaling that they are going to fight. Okay, and actually afterwards they also launched some patent infringement actions, and they put a lot of action prior to the Kodak entering the market, because they had some cameras that were waiting on the shelf. They put them on the market. They throw the new cameras, new film on the market. And this is what happened is typically you do it when you have a new market entrant because you want to respond to that move, but they did that in advance. So when you think about the game, that the way they changed the game, it doesn't fit to the picture that we have discussing or I presented before. Because what they did, the way you can imagine it, is that they changed the payoffs, but in this very special way, because this is sort of a talk that they were sending to the market, cheap talk, but it costs something, because making statements by the founder can be punished by the market afterwards. So if he doesn't stick to the promise, so this is costly, at least personally. They moreover throw the cameras on the market, which they didn't have to do. So what happened can be captured by the game tree presented in the slide, and so they can. I call it burn the money, $1, or they can no burn the money. So if you look at the lower part of the tree, or upper part is just where we burn the money. What changed is the payoff changed slightly, right? So for Polaroid, the numbers are not -1 is -1.1, instead of 1 is 0.9, and instead of 2 is 1.9. So what happens is by changing every payoff from every action in the same way, they did not really change the incentive. So it's again still the same thing. Acquiescing is the best to do for Polaroid, and challenging is best thing to do by Kodak. Okay, now when we look at the two strategies, whether to burn the money or not, of course it doesn't make sense to burn money, because burning money like loses some. You make something, some payoff disappear. Now, so the idea here is it doesn't make sense really to burn the money. So Kodak should enter the market independently of what Polaroid did, and Polaroid should acquiesce afterwards. So this is the game tree. But what happened is Polaroid burned money. So how can this be interpreted? So very important thing is to make here, and it brings us back to the first slide when were discussing solutions to games. I said that there are some ideas, some requirements, some elements that need to be satisfied. So you need to know the game, you need to know the payoffs, you need to know that your opponents are rational, because you know they are rational, then they are optimizing their payoff. What happens here, Polaroid, by burning money, sent signal to the opponent that they are not rational, right? And because of this, the idea, this the basis on which Kodak was evaluating the interaction has disappeared. So now, if Polaroid is not rational, everything could happen. Everything and anything could happen. The interesting thing is that Kodak did not enter the market, and therefore the move by Polaroid was not really irrational, because this irrationality, like strategic irrationality, led to a situation that was better for Polaroid, which is then rational. But this is what you can learn from the particular example of Polaroid and Kodak, that the game can be changed in a very fundamentally different way from the changing the payoffs, own payoffs of others, fixing or let's say taking a technology that is more expensive, or setting the standards, like in the case of Monsanto. You can also play irrationally. Again, this strategy includes also some risk, and that you can actually be very clear about. But this is what happened. Of course, this is one interpretation of the facts. There are alternative ones. I also refer you to a case by Harvard Business School Publishing that deals with the case. There are more details, more numbers that you could probably learn something more. But this is an interesting case for strategic management, and it is an interesting case for me to discuss as a game theory as a tool to analyze strategic interaction. I covered the 4 parts. Just a short summary, and afterwards you will have the chance to ask questions if you're interested. If you think about the solution concept, it's not as obvious as it looks like. They are very simple. So Nash equilibrium is a simple and powerful notion. John Nash received for this particular development, for Nash equilibrium, a Nobel Prize. So together with Reinhold Zelten and John Harsanyi in 1994. Okay, so this is something that is very strong, very fundamental. But the question how to find a Nash equilibrium is not an obvious one, and what it requires is a lot of thinking, a lot of introspection. Might be a bit easier for sequential games, but then you have to make sure when you model it, what do people care about? Is it money, like in the Ultimatum game? There are some probably other aspects, and when analyzing, is backward inductive solution one that we can accept? For the points 2 and 3, we see that really the point for business students of learning game theory is not just to understand what will happen, but the more important point is, if you know what will happen and the rules of the game are in many situations flexible, you can change the game in your favor. So this is what the case of Yaki and Zenit showed, and the thread game and the different ways to change it. And it was applied to the case of Polaroid and Kodak. That is what I have prepared for you for today. I thank you for your attention.